Here we have a 3x3 system of linear equations. I solved this already in another video. I'm going to solve it again here. I'm going to do it very quickly, whereas the first time I solved it I went through it fairly slowly and yacked about it a lot. So when we solved this system of linear equations, we basically had three things that we did. Actually, when I solved this one, I only used two things. I added a multiple of one row to another, and I multiplied through by a non-zero constant. And another thing you can always do is swap the order of the equations. So this system, if I wrote these three equations in a different order, I think it's fairly clear that it would be the same system. So it wouldn't matter which equation you write first, which equation you write second, which equation you write third. Also, if I take any one of those equations and multiply through by a non-zero constant, it doesn't change the information in the equation, and so I think that one's fairly obvious. It doesn't change the system. And the last one, which is actually the most important one, is I think the least intuitive. You can also add a multiple of one equation to another. So like when I solved this in the previous video, the first thing I did was I added the first equation to the second equation. So only the second equation is going to change. The first and the third will not change. And if I add this equation to this one, negative x plus x is 0x, which I'm not going to write. 3y minus 2y is y. And 0z plus 3z is 3z. And negative 4 plus 9 is 5. And so that's adding the first equation to the third equation. And then the next step, which was the sort of strange step. Actually, the first time I solved this in the video, I multiplied the first equation through by a negative 2 to get a negative 2 on this x. And then I added that resulting equation to this. And then I divided back through by that negative 2 to get back to this original equation. But we condensed that down into one step, which was just adding negative 2 times the first equation to the third equation. So doing that in 3 steps is somewhat easier than doing it in one step, but it's going to be important to build that skill. So the next step I'm going to make is to add negative 2 times that first equation to the third equation. So it's only the third equation that I'm doing something to. And I get this plus negative 2 times that is 0, this plus negative 2 times that is negative y, this plus negative 2 times that is negative z, this plus negative 2 times that is negative 1. And then I can say add the second equation to the third equation, so only the third equation will change this time. Second equation doesn't change because I'm using it, but I'm not changing it. And then so you'd have this plus this is 0, this plus this is 2z, this plus this is 4. And then the last step we did in that video, running out of room here, was to multiply the third equation through by 1/2 or divide both sides by 2. And so and then once we got it into this nice stair-step sort of construction, it was easy to solve. We know z is equal to 2, we plug z equals 2 in there, we get y equals negative 1, we plug in y equals negative 1 in here, and z equals 2 in there, and we get x equals 1, I think. And so we're done. But you can see that in order to do this, you've got to write down a lot of things over and over again. And really a lot of the things that you're writing are just repetitive, and you really don't need them. So I'm going to put this into what's called an augmented matrix. So instead of knowing that this 1 is being multiplied by x, and this negative 2 is being multiplied by y, and this 3 is being multiplied by z, we know that because it says it right there. In the matrix, we're going to drop off the variables, and we're going to know which number is being multiplied by which variable. We're going to know that information by where it is in the matrix. So the first column will be the x column. The second column will be the y column. The third column will be the z column, and there's no z there, so this is a 0. And then the fourth column will be the numbers on the other side of the equal signs. And so this is what you call an augmented matrix. This is how I like to write my augmented matrices. Some people like to make a distinction in their matrices between what's called the coefficient matrix, the part of the matrix that consists of the coefficients on the variables, and the constant matrix by putting a vertical line down here. I have mixed feelings about that line. I don't love the way it looks. It's also something extra to write, so I don't tend to write it. If you want to write it, you can. If you have experience with stuff before and you're in the habit of doing it, it's fine. If you prefer to, make a separation between the coefficients and the constants over there, that's fine. With or without this vertical line. This is like vertical line optional here. So this is called an augmented matrix. And essentially I'm going to do the same thing with this augmented matrix that I did with the system of equations when it had its variables in it, when we were looking at them just like equations. So there are what are called row operations that you can perform, and they correspond to the three things I said you could do to the equations. You can swap rows, you can multiply a row by a non-zero constant, and the key one is you can add a multiple of one row to another. So those are the three row operations that you can do, and if you do nothing but those row operations, you're going to end up with a matrix that contains the same information as the original matrix. And if you play your cards right and you get your matrix in that nice stair-step form, then you can get the solution. You can really read the solution right off the matrix. So essentially my row operations here are going to follow what I did with this the system with the variables in it. So my first step is going to be to add row 1 to row 2. So it's row 2 that's going to change here, and only row 2, just like it was the second equation that changed there. So the first row, I'm going to leave out my vertical line now because, like I said, I don't really like it. I'm going to do this plus this is 0, this plus this is 1, this plus this is 3, this plus this is 5. So you're doing -1 plus 1, 3 plus a -2, 0 plus 3, -4 plus 9. And then I'm going to get my 0 here, just like I got rid of the x there. I'm going to add -2 times row 1 to row 3. So that's my next step. So the only thing I'm doing something to is row 3. So row 3 is the only row that's going to change. So I get 2 plus a -2 times 1 is 0. -5 plus -2 times -2 is positive 4. -5 plus 4 is -1. 5 plus a -2 times 3. -2 times 3 is -6. 5 plus -6 is -1. 17 plus a -2 times 9. -2 times 9 is -18. 7 plus a -18 is 7 minus 18 is -1. And then I'm going to do the same thing that I did to get to here. I'm going to add row 2 to row 3. And so it's only row 3 that's going to change because it's the only thing I'm doing something to. So I'm going to get 0 plus 0 is 0, -1 plus 1 is 0, -1 plus 3 is 2, -1 plus 5 is 4. And then in the next step, I'm going to do what I did to get to here. Multiply row 3 by 1/2. And I'm saying I'm multiplying row 3 by 1/2 because the row operation is specifically, you can multiply. I mean, really it's the same thing as dividing both sides of the equation through by something. So you get 1, -2, 3, 9, 0, 1, 3, 5, and 0, 0, 1, 2. And so if you were to translate this back to a system of linear equations, you'd be right here. And I had very many fewer pen strokes, or in my case, I guess pencil strokes, to get to there. And I've got this nice stair-step thing. This is called row echelon form, where I have zeros down here below this diagonal. And that's nice. But you know what? I'm going to keep going because these row operations are so nice. And if you remember, the back substitution got messy and there were arrows all over the place. And it was just kind of not a very tidy way to go. So what I'm going to do is I'm going to use this 1 right here to get rid of this 3 and this 3. So I'm going to add -3 times row 3 to both row 1 and row 2. So I'm doing two things here at once. I'm starting to work up, which tends to cause people a little bit of trouble, and I'm also doing 2 row operations in one step, which is legal as long as you're not trying to use a row that you've changed in that step on another row. Then it gets dangerous. But I'm just using this second row to get rid of this 3 in the, I'm using this third row to get rid of the 3 in the second row and the 3 in the first row. So if I do, so this last row is the only one that's not going to change because I'm using it to do something to row 1 and row 2. So row 2, then I'm going to do this plus -3 times this is 0. 1 plus -3 times 0 is 1. 3 plus -3 times 1 is 0. 5 times -3 times 2 is -6 plus 5 is -1. And so this 0 comes from this plus -3 times this plus -3 times that is 1, this plus -3 times that is 0, which was the whole point of choosing -3 here. 5 plus -3 times -2 is 1. I'm going to do the same thing with this row. So you're going to get this plus -3 times that, this plus -3 times that. And what's nice about using this third row now is I have zeros here and here, so my first 2 column entries in the first row are not going to change. This plus -3 times that is 0, which is what I wanted, and this plus -3 times that, -3 times 2 is -6 plus 9 is 3. And then my last step here, this is a little bit messy because I didn't plan my space very well, is I'm going to add, I want to use this 1 right here to get rid of this 2, so I'm going to add 2 times row 2 to row 1. So the only row here that's going to change is the first row, so the second row will still be the same. And so I'm going to do this plus 2 times that is still 1 because 2 times 0 is 0. This plus 2 times that is going to give me 0. 0 plus 2 times 0 is 0. 3 plus 2 times -1 is 3 plus -2 is 1. And so if you look at this now, this is really beautiful. This is what they call reduced row echelon form because I have essentially zeros everywhere I can. And if I translate this back to a system, this first equation says, this first row is the equation x equals 1. The second one is y equals -1, and the third one is z equals 2. And so there you have it. One example of solving systems of linear equations using matrices. Okay, very good.